Welcome to today's online class, children. Today we are going to see uh, the topic, very important topic, that is scattering of light. In particular, atmospheric scattering we are going to see today. Okay, now to start with, what is scattering of light? See, actually scattering represents basically the change in the direction of light. Change in the direction of light. And this scattering of light is not new to you. Actually, you would have studied in your 9th standard lower class what is called Tyndall Effect. What do you mean by Tyndall Effect? Let me first recall it before going to atmospheric scattering. So, see here, what do you mean by Tyndall Effect? You see here, when a beam of light is passed through a colloidal solution, see here, when a beam of light is passed through a colloidal solution, the colloidal particles, the particles of the solution, okay, scatter the beam of light, okay, and hence the path of the light becomes visible. It scatters, okay, that is why, what is it? The path of the light becomes visible in the solution. If you see here, see the path of the light, you can see here now in this case. See, here the path of the light is visible because of scattering, that is visible in the solution. It is purely because of scattering of light by the colloidal particles in the solution. Okay, so this effect is what is called Tyndall effect. This is what is called Tyndall effect. Okay. Now, actually, see, you can even see the very Tyndall effect examples, you see, can be seen. The Tyndall effect can be seen when light enters a room through a small hole, a small window, whatever, a small hole, due to scattering of light by the dust and smoke particles. Okay, the light is coming. Here you see it spreads enough. Here you see, if you see this, the light nicely it spreads like that. Okay, so why? It is only because of scattering of light, okay, due to, see, the dust particle in the room or smoke, dust, whatever is there, because of that dust particle, that smoke, whatever the particles are, what is the scatterer? They are called a scatterer. So these, when it falls, the light falls on this scatterer, it nicely, what is that? It scatters the light, and hence, see, this is, you can see that the light gets diverged. Now you can see this one. Okay, therefore this is also one of the very important example of Tyndall effect. Okay, then next one, you see, Tyndall effect can be seen in the dense forest due to scattering of light by water droplets in the mist. See here, very how nicely it is shown. You see, there is the forest. When the sunlight is coming, okay, therefore there will be, what is in the forest, there will be water droplets will be suspended, okay, and in the mist. Okay, these water droplets acts as a scatterer, and because of that, you see here how nicely it is shown. So the light gets scattered in different directions. Okay, so these are all the very important examples that in day-to-day life that you can see. Okay, by examples of Tyndall effect. Okay, right. So these things that you have idea about this Tyndall effect, because you have studied in your 9th standard and lower classes, right? Now, what we are going to see here is atmospheric scattering. It is also scattering of light, but what is called atmospheric scattering. So, what is atmospheric scattering? See, actually, the light with, see, in the atmosphere, the actually, see, you know, light from the sunlight, from the sun, it has to travel a large part of the atmosphere, correct, to reach us, before reaching us. So the atmosphere, it has large number of molecules and numerous small particles that are present in the atmosphere. Okay, so when the sunlight comes through the atmosphere, it gets scattered by those gas molecules or small particles which are suspended in the atmosphere. Okay, So that is why most of the beautiful phenomena like blue color of the sky, okay, and you can say red hues of sunrise during sunrise and sunset, okay, these things, and even you can say clouds, white color of the clouds, okay, these are all due to the scattering of sunlight by the atmospheric particles, okay, therefore now this atmospheric scattering, it was first studied by Raleigh, okay. So this we are going to now, scattering of light we have seen. Now we are going to see what is atmospheric scattering. So atmospheric scattering means which is scattered, sunlight is scattered by the atmospheric particles, okay. Therefore this was first studied by a scientist Raleigh. According to him, see, when the sunlight is traveling through the atmosphere, okay, the atmosphere, see, definitely the light gets scattered by the gas molecules which are present in the atmosphere, right? But the sunlight has several colors, you know very well. Why? It is a white light. So all visible spectrum, every color is there, right from violet to red, okay. But according to Raleigh, he told that the intensity of the scattering, that is what is called, see, intensity of scattering of white light, okay. So that is IS, intensity of scattering, is inversely proportional to the fourth power of the wavelength of light. Very, very important. Intensity of scattering, okay, of sunlight, that is of intensity of scattering of light, white light, okay, whatever is, it is intensity of scattering is directly, it is inversely proportional to the fourth power of the wavelength. That is number one. It was given by Raleigh. Therefore intensity of scattering is inversely proportional to fourth power of the wavelength of the light. More the wavelength, less will be the scattering. That is why it is given. Intensity of scattering is, what is that? More the wavelength, less will be the scattering, and vice versa. That is number one. Number two, second condition. See, even this is what is called, the intensity of scattering is inversely proportional to the fourth power of the wavelength. This is what is called, you can say it is selective scattering. Selective scattering, Monica, what is selective scattering? Selective scattering means a scatterer. The scatterer, that is gas molecules which is in the atmosphere. Okay, these they see which wavelength is coming. They will select the wavelength. Okay, and if the wavelength is very small, okay, it will be nicely scattered. If the wavelength is less, the wavelength is very large, then okay, scattering. What is the intensity of scattering will be, they will be scattered less. Like that, they will select the wavelength, accordingly they will scatter. That is what is called selective scattering. But what is the condition for selective scattering? Now, see, condition for selective scattering. What is that? See, what is the condition here is, see, it depends very much on the size of the scatterer. What do you mean by scatterer? The particle which scatters light. Okay, that is what is called scatterer. The size of the scatterer. Okay, so it should be, that is, let it be X. Let me have this one as X. Okay, size of the scatterer, that is X, S, should be very much less than wavelength. It should be very much less than the wavelength of the light which is being scattered. So, condition for selective scattering is the size of the scatterer. It depends very much on the size of the scatterer. If the size of the scatterer is very small with respect to, when compared to the wavelength of the light, then okay, that scatterer, that particle, okay, that actually scatters the light according to this, what is the condition, what is the I? Yes, intensity of scattering is inversely proportional to fourth power of the wavelength. It follows. Okay, size of the scatterer is very small means it follows selective scattering. But if the size of the scatterer is very big means water droplets, dust particles, usually lower atmosphere, no, the lower atmosphere. Upper atmosphere means gas molecules are there, their size is very, very small. Okay, but lower part of the atmosphere, if you see, it is filled with, you can show the dust particles are there, and okay, and water droplets will be there, and even the carbon components, small and ice particles will be there. Okay, and these are all, the size is very big. Okay, I'll know it is big, so what they'll do, they won't go for selective scattering. What do you mean by they won't go for selective scattering means, what do you mean by that? All the colors will be uniformly scattered. It won't see, okay, yeah, what is the wavelength? It won't bother about the wavelength. Selective scattering means the wavelength is small, scattering will be more. But in the case of uniform scattering means, what is that? It won't even see if x is larger than lambda, then what is that? Uniform scattering. Uniform scattering, that is no selective scattering. Are you following? So this is very, very important. These are all two conditions. What is that? According to Rayleigh, intensity of scattering is inversely proportional to fourth power of the wavelength. That is what is called selective scattering. And selective scattering is possible only with respect to size of the scatterer. The size of the scatterer is very much less when compared to the wavelength of the light, then it will go for selective scattering. If it is big, then it scatters all the light uniformly. Are you following, children? Therefore, with respect to this, we are going to see, okay, different day-to-day life, what are all the happenings here. Okay, so some applications of this atmospheric scattering of light. Applications of scattering of light, that is atmospheric scattering. Okay, right. Now see what are all the applications. Now number one first, okay, blue color of the sky. What is the reason? What is the reason for blue color of the sky? See, it is due to, no doubt is due to the scattering of sunlight. The light which is coming from the sun, it gets scattered. Okay, but when the light is coming, when the light comes from the sun, okay, while traveling through the atmosphere, Earth's atmosphere, it gets scattered by large number of molecules in the Earth's atmosphere, right? Okay, but here, it is in the uppermost atmosphere, where it has to travel a very long distance in the atmosphere. Now, there, that is gas molecules. Usually, what is it? It consists of small gas molecules are there, and these molecules are the gas molecules. The size is less than the wavelength of the light. Wavelength of the light, the wavelength of the light means, see, you see, it is a visible light. I am telling about the visible light. Visible light means first one, the maximum wavelength, red. Red will be around, you can say 750 nanometer around. Okay, so it is 750 nanometer, but there's a range. Okay, maximum you can say up to 750 nanometer. Nanometer mone kya hota? 750 into 10 power minus 9 meter. Okay. Okay, now next one is the other color, extreme color means violet, na? So lambda violet, okay, that is around, I can say it is 380 nanometer. And what is for blue? Blue, it is around 450 nanometer. Okay, now you see, when the blue, see why the sky appears blue here? See, when the light is coming through the atmosphere, okay, the molecules, the gas molecules, okay, they follow selective scattering. They follow selective scattering. How? The intensity of the scattering is inversely proportional to fourth power of the wavelength. Na? So इसमें तो fourth lowermost wavelength is what is it? Violet. Okay, but the next one is indigo, then it is blue. Therefore, you see here, when the light is coming through that, passing through the atmosphere, the lowest wavelength will be scattered in the atmosphere itself. The outer atmosphere. The outer atmosphere, when the light is entering and the sunlight is passing through the atmosphere, what they'll do, the scatterer, that is the gas molecules, the atmospheric particles, they follow selective scattering because their size is very much less than the wavelength of the light. Therefore, what they'll do, they undergo selective scattering. They will see the lowest wavelength. Therefore, what is that? Violet. Violet will be scattered a lot. After that indigo, then it is blue. Therefore, the upper atmosphere will be fully scattered with what is that? Violet, indigo and blue only. Okay, that is why when we see from here, it appears blue but not violet now. But actually, violet is only having the lowest wavelength, but the sky appears blue only. Reason, see here, I will show it to you here. See here, this one. Okay, see, the light is coming. See, the light is coming from the sunlight. Okay, it has all the colors. White light, no, it has all the colors. No, sunlight has all the colors. Therefore, red, yellow, green, everything is coming here. Here, last one, the lowest one is violet. But violet, you see, sunlight. Okay, it consists of also, it sends only less of violet. See here, you see, less of violet, it sends more of blue only, the color. Okay, so even as such, naturally, sun sends, it sends lot of blue color but less of violet. That is number one. Why? I am giving you the reason why the sky appears blue. Okay, as I told you, what is that? Intensity of scattering is inversely proportional to, as I told you, inversely proportional to the fourth power of the wavelength that already we have seen. Okay, therefore, intensity of scattering is proportional to fourth power of the wavelength. Therefore, fourth power of the wavelength, it should appear, as I told you, as the light is coming, of most of the least wavelength lights, colors will be scattered in the outer atmosphere. So, if you see from here, from our surface of the earth, it appears blue in color. It is not appearing violet, or it is not appearing indigo. Why? Because sun, it sends less violet color, and but it sends more of what is that? Blue color. That is number one reason why it is blue in color. And another one is, very important one is, our eye. Our eye has millions of cones, I think you see, and they are actually very much sensitive to dominant color like blue. Our eye, naturally, it is very much sensitive to, what is that? Blue color rather than violet and indigo. Our eye is sensitive only for, what is it? Sensitive to blue color, then the other, violet and indigo colors. Actually, first violet and then indigo, then only blue. Okay, but these two colors, as such, sun is also sending more of blue than violet and indigo. And number two is, our eye is sensitive to what is a dominant color out of this violet, indigo, blue, which is dominant, it is blue. Our eye is very much sensitive to blue. That is why we see only, what is that? Blue color. The sky appears blue only because of, what is that? Atmosphere is scattering, that too Rayleigh scattering, that is selective scattering. Intensity of scattering is inversely proportional to fourth power of lambda. And why not it is violet? Because our eye is very much sensitive to blue color rather than violet. Okay, that is why it appears blue, not as violet. Not as violet. Hope you are following this. Right. Next one is, why, see, let me go for next application. Okay, second application is, okay, you can say white color of cloud. White color of cloud. Okay, white color of the clouds. Why? What is the reason? See, usually the clouds are at much lower height. Let me see, I'll show it to you, this one. See, the clouds are actually at they are at lower heights. Okay, and these clouds are seen, see, it is very, these clouds are seen, okay, due to the scattering of light from the lower part of the atmosphere. Scattering of light, okay, so that is scattering of light due to, what is that, lower part of the atmosphere, due to the scatter. It is, see, these clouds are seen due to the scattering of light from the lower part of the atmosphere, and this lower part of the atmosphere contains large amount of dust particles, because lower part of the atmosphere, when the clouds are seen only lower, clouds are only at the lower height, okay, therefore much lower height actually. Because of that, what is that, at lower height, what is that, the it has lots and lots of dust particle, water droplets, okay, and even some ice particles, okay, and these particles size is very big. Size, therefore here the size of the particle, that scatterer, here scatterer, here, what is a scatterer? It is a lower atmosphere mein to, what is that, it is filled with a lot of dust particles are there, water droplets are there, whose size is very much larger than the wavelength of the light. Okay, therefore it won't follow selective scattering. It won't follow selective scattering, but all the colors, it won't see which color is falling. White, sunlight is falling now. Sunlight has all the colors now. So in the previous case, why does the what is the sky appears blue? Isme to, what is that? The scatterer is very much bothered about the wavelength. Okay, it sees the wavelength, and lower the wavelength, now more will be the scattering. That is why upper atmosphere, all the lower wavelengths will be scattered in the upper atmosphere itself. That is why when we see from here, sky appears blue. Okay, and I told you why not violet and all, the reason I told you. But now, it is, the clouds are in the very lower part of the atmosphere. Lower part of the atmosphere has large number of dust particles, droplets and all. And their size is very much larger when compared to the wavelength. So, they don't go for selective scattering and all. They won't see the wavelength. All the color, with the white color, the sunlight is white now. So, all the colors will be uniformly scattered. So, they will go only for uniform scattering. Therefore, all the colors are, okay, equally scattered. Okay, therefore equally scattered. That is why, okay, the clouds are appearing white in color. Are you following? Clouds are appearing white here. Why? The reason is, droplets scatter all the wavelengths of visible light, creating the appearance of white cloud. All the, it equally scattered. No partiality here. No selective scattering. That is why, because the droplet, the scatterer size is very big. The scatterer size is very big when compared to the wavelength. Are you following? Then, third, very important. See, what is the third application? Third application is, see, why, see, reddish appearance. The sun looks reddish. Okay, so orangish, reddish, slightly orangish also, reddish at the time of sunrise and sunset. Okay, I think this is a very common what is appearance. Sun looks reddish at the time of sunrise and sunset. Very, very important. Why? What is the reason? See, I'll let you know now. See here, you come back to this diagram. You see, very, very important. See here. Okay, see, during the sunrise and sunset, this is our earth. You see here, it is the earth. Okay, see here how nicely it is shown. This diagram you see. Okay, therefore, during the sunrise and during the sunset, Okay, both the time, okay, the sun is near the horizon. Sun is near when the I think I told you in the refraction, if the sun only appears only when it is coming above the horizon, when it goes below the horizon, sun is invisible, right? But when it is at the time of sunrise and sunset, it is, what is it, the near the horizon. Okay, therefore when it is near the horizon, you see the rays from the sun here, the rays from the sun have to travel a long distance. It has to travel a long distance, travel a larger part of the atmosphere. Okay, after that only it reaches to our eye. It reaches to our eye. Are you following? Because it is at a very large distance. This the sun at the time of sunrise and sunset. Okay, the sun is near the horizon. Okay, therefore, what is that? It has to travel a very large distance. Okay, to reach our eye. So large part of the atmosphere it has to travel when it is coming. So what happens as it is traveling? Okay, most of the, because it is everything is atmosphere, most of the blue color, violet, yellow, violet, what is it, indigo, everything will be scattered in the upper atmosphere itself. Okay, so everything will be scattered there. Okay, but which light is somehow it is able to manage to come to reach our eye is red. Which color is reaching? Which color is reaching here? Only red. Okay, yeah, orange, orangish. Okay, so these colors, because they are having more wavelength, more lambda. So all the blue color, violet, everything, they will be scattered. Even you see yellow, some part is yellow also. No, so yellow is also, you know, what is a WebGR? Violet, indigo, blue, green, yellow, orange, red. So these three, you can say red, orange and yellow, they are the higher wavelength side, right? So that these colors somehow, because all the other lower wavelengths will be scattered in the outer atmosphere, in the outer atmosphere itself. So therefore, which color is successful in reaching our eye? It means red, orange, okay, some part of yellow. Okay, that is why it is, what is that? It appears slightly reddish, orangish during sunrise or sunset. Are you following? Because it is, the sun is near the horizon. Okay, therefore, what is that? The light has to travel a large part of the atmosphere. As it travels, most of the lower wavelengths will be scattered in the outer atmosphere. Only some color, the red, probably that is maximum, that is red color and orange color. Okay, it somehow, because its wavelength is more, they manage to reach, they manage to travel the atmosphere and it reaches our eye. Okay, that is the reason, right? But at noon, at 12 o'clock, at noon, if you see the sun, it will be white in color. It will be white in color. Correct? At noon. So why is it appearing white in color? Why? Because at noon, okay, the sun is actually, it is very close. It is very, very close to our head. Actually, it is just above. Okay, therefore, what will happen? Because they are very much nearer. See, if you see the distance itself, see noon, the distance of the sun from the our earth surface is very, very less. Okay, therefore, during actually noon, even all the colors somehow they manage to reach the surface, reach our eye, reach the surface of the earth. Okay, why? Because even the violet, indigo, blue, all the colors, somehow, because the distance of traveling is very less here. When compared to this, during sunrise, sunset, they have to travel long distance. That time everything, all the lower wavelengths will get scattered. But here, during noon, it is just above our head. So very close when compared to sunrise and sunset, during noon, the sun is very close to us. So because that time, almost all the colors here also white color only it is giving, here also white color when the sun is giving rise to, it gave only white color is coming from the sun. So even here when the white color it comes, but here because the distance is very less, even all the colors, right from violet to red, all are somehow it is managing to reach our eye. Are you following? Every color is coming to our eye, so that what is that? The sun appears white during noon. Is it clear? Hope you are following, children. Right. Next one, you see. Have you seen that? Here, see, danger signals, no? The danger signals are, next one, okay? The danger signals are red in color, no? Have you seen this? See, and one more very important thing, that is, see, before that, okay, see here, danger signals are red. Why? What is the reason for that? Definitely, see, atmospheric scattering, that is selective scattering. See, the red color will be usually right from all the visible spectrum, right from violet, indigo, blue, green, yellow, orange, red, and in all the out of these visible colors, visible spectrum, all these colors, red lambda r is very much large. Lambda v is least. Correct? Therefore, lambda r is very much larger than lambda v. Okay, and all the other colors, maximum wavelength is only red color is only having. Okay, so more the wavelength, you know that selective scattering, less will be the scattering by Rayleigh. That is why danger signals are usually red in color. Why? Because the light from the red light can travel a long distance without getting scattered. Even by the scatterer, so many scatterer will be there. But the red light somehow it can, what is that? Because your intensity of scattering is inversely proportional to fourth power of the wavelength. Wavelength of red is very, very large. Okay, therefore the scattering will be least for red. That is why red light, okay, if the danger light is red in color, then that color, red color, can travel a very long distance without getting scattered. So that even if a person is at a very large distance, he can see that red color, okay, that a danger signal even from a kilometer, 2 kilometers away from the signal. Are you following? Why? Because the red color can travel a long distance. But for example, if it is violet or if it is blue, definitely it cannot reach. If the observer is at a very large distance, okay, therefore he cannot see the danger signal at all. Why? Because the color is blue. If the color is blue, what happens? Before reaching the observer, all the color will be scattered in the atmosphere itself. But if it is red, it will be least scattered. Therefore, definitely red color, definitely it will reach the eye of the observer. Are you following? That is the reason why all the danger signals are actually red in color. Very, very important application. These are day-to-day life people are using here. Is that okay? And another one you see, I think you would have seen in trucks and all, no, big trucks and all. See, when they are carrying some goods. Okay, and if the whatever items if they are taking rods and all, steel rod, whatever is that, okay, it's if sometimes the whatever material they are taking, that may be projected outside the truck. Okay, so if the truck is actually, see, that is very, very important. See, if the truck ends here only, okay, so but okay, now but the items here may be projected outside the body of the truck. There are sometimes, okay, therefore if it is projected, you see, but you know very well, I think in the truck at the back of the truck, there will be red light will be there, no? The red light, why? Because even any person, any car or something is coming here, okay, so they can very well see. Okay, red light is there, 2 red lights are there, therefore some, what is that, car or some 4-wheeler is going. Okay, they can sense it, red color, because it is red. Red can reach a very large distance, so the driver can see. Okay, but here the material is projected outside, no? that iron rod is projected outside means for a person here, he can see only red light at that too during night and all, no? Okay, he can see only red light, so he can see, okay, up to this this much of this part of the rod which is projected, he cannot see in the dark. Okay, he can see only the red light, so that part won't be visible to him, so it may lead to accidents. Are you following? So because he is not able to see, this much part is not visible to him. Okay, so to avoid that only, usually it is a traffic rule, you know. So what happens, the red see in this part, which part, the here is there, no, whichever is projected here, if something is projected here, okay, if some material is projected here like that, okay, what happens, a red cloth or some red color ribbon or something like that, it will be hanging here. You would have seen this one. Okay, therefore it will be hanging here, some ribbon. It is definitely they have to tie it here. Okay, why at the edge of the here, at the edge of the material, okay, which is projected outside, there if red ribbon is hanged, then the person who is coming at the back, he can see, okay, so this is the red color, this that is red light, he can see from the what is the that is a light in the at the back of the vehicle, that also is visible, and after that he can even see this red ribbon that is hanging. So from that, but he cannot see all the rods and all. Why? Because their color is different. No, it is black, so it cannot travel. But red means it has more wavelength, so it can definitely reach the eye of the observer, the person who is coming at the back, so he can understand, yes, it is not only the truck, but there is something is projected, the ribbon is hanging, so up to that there is some material, so you have to be very careful. Okay, so these are all the very important, that is why your danger signals are red in color, and what is that, there is a red ribbon that is tied in the trucks. Okay, these things are only because of, what is that, it is all the application of, what is that, scattering of light. Is it clear, children? Right. One more very important thing that I want to tell you here. See, the sky appears dark black for astronauts. Okay, that is very, very important here. Sky appears dark, black actually. Sky appears black or dark for astronauts. Okay, what is the reason? Astronauts. Okay, what is the reason for that? Reason for that? Why? What do you see here? The reason is space has no atmosphere. Astronauts. Okay, wait. See, what is the reason? See here, space has no atmosphere. Space, because they are in space. Okay, so space has no atmosphere. Okay, so light rays from the sun are not scattered at all. There is no scatterer, no atmosphere, so no scatterer. Therefore, what happens? Therefore, the light coming from the sun, okay, is not at all scattered in the atmosphere. Okay, no scattering of light takes place. That is the reason why, okay, the sky appears black for astronauts. Is it clear, children? Okay, so this is about scattering of light. Okay.